Alright, I promised this was coming, and now we are finally ready. Let's talk about how to write functions for real in assembly. I won't sweep anything else under the rug. I won't tell you to memorize anything else. I will explain it all. Alright, I'll do my best. So, yeah, the first thing I want to talk about is the stack. Like, we were manipulating SP, and I want to go and take a deep dive into that so that we all understand what's happening. Alright, so the stack, first of all, we should have seen diagrams like this, right, in like CSCI 40 and CSCI 41. Every time we call a function, we save our work. We know where we are on this place called the stack, right? So like here's the main function. That's like the first function that gets called. And also inside of each of these stack frames, we call them, main may allocate some memory for itself, some local memory for its local variables. So main might make a local variable, and it might also needs to save some other stuff on the stack, like a return address. All right. And then main might call another function. And let's say we have another function called like int foo that like declares a local variable and does some stuff with it maybe. And so what I'm going to show you is that, well, when you make the call, first of all, for main, from code in main into foo, like we add a stack frame for foo, and it starts allocating some memory. First of all, foo is probably going to need to save the return address, that thing that's in LR in case it calls any of its own functions. And it's got to make room in local memory, which is on the stack, right, for its X variable as well. So all these things need to happen. And then when foo returns, like it puts a return value in X0 or whatever, and it's got to somehow pop itself off the stack. And now we're back in main, and now it's like foo never happened. Right? All that memory goes away, gets reclaimed. So I need to show you exactly what's going on in these diagrams, right? You know how to draw these diagrams by now, but like, how does it really work under the hood? How is stuff being allocated on the stack and being reclaimed? All that fun stuff. All right. So yeah, let's go back to the function call stack. What it does is it holds your local variables. It's space, right? It's a space in memory. It holds your local variables and information about where those functions that have been called need to return back to. All right. So every time you call a function, it creates a stack frame. Like main gets called, it creates a stack frame. Foo gets called, it creates a stack frame. All right. That's always going to happen, unless for some reason you don't need to allocate any stack memory, which is usually like very, very rare. All right. So every function call, just pretend it creates a stack frame. And at the very least, for us, it's going to hold a pointer to the instruction to jump back to. That LR value should always probably be saved away. All right. So yeah, ARM might do some things slightly differently. Like you don't technically have to save LR if you don't call any functions, but let's just pretend that's something you always have to do. All right. And it's not going to hurt you in this class. Some other architectures require it, in fact. But yeah, every function call creates a stack frame, which at the very least is going to hold a pointer to that instruction that you need to return back to. All right. And we're going to save that in all of our functions anyway in this class. All right. So for example, let me make a stack diagram that's color-coded. So let's say that main starts us off. Main is the first function that gets called, and main will be red. So here's main's stack frame. And then let's say that main calls a foo function, and so a new stack frame will get added to the top there. We'll allocate some memory on the stack for all of foo's local variables and its return addresses. And then let's say that foo calls bar. So somewhere in the foo function, while we're executing, while its stack frame is still going, foo calls bar, the bar function, and then it makes some space for itself on the stack as well. All right, and let's pretend that foo and bar have one local variable each. So like foo has an X variable, bar has a Y variable, and everybody, regardless of whether they have variables or not, are still storing the return address on the stack. The return address where it needs to jump back to once this function returns. All right, that's going there. Return address, return address, return address, and they're all different, right? Because bar needs to return to some code in foo. Foo needs to return to some code in main. Main needs to return to some code in like underscore start, stuff like that. And as let's say bar does all its work, it needs to return back to foo, right? It knows where to go back to by looking in the return address place on the stack. That's where it's going to jump to. That's how it knows to jump back to foo. And then it also needs to clean up the stack by removing everything that it's ever had here. So it pops everything off that stack. right? And that function call stack, it pops its own frame off, and now we get back to foo, and it's like nothing ever happened. There's no extra memory that's been here reclaimed anymore. It's like the call never happened, though it did. Okay, so that is a little bit more information than we saw in CSCI 40 and CSCI 41 already. Okay, let's go even deeper now. All right, so at a lower level, what's going on when functions are being called and returning? So the stack is growing downward. That's a new thing. That's a very interesting idea. So the stack is growing downwards towards lower addresses. So like here is main stack frame. Like here's kind of the drawing. Main's return address is being stored at this address, let's say. And then foo is pushing things onto the stack at a lower address. Do you see that? Lower addresses. Lower addresses. And these are hexadecimal addresses, so 8 bytes each. That's why it might not make a lot of sense. 28 to 30, they're the same size thing. Hexadecimal, all right, that's why. So main stuff, foo stuff, growing towards lower addresses. The next thing goes on a lower address. The stack goes downwards, we say, towards lower addresses, okay? So that's how that works. And where the top of the stack is referenced using SP. All right, that's something we've done already. Now I'm showing you exactly what's happening. You always know where the stack is, where the top of the stack is by referencing SP. So SP is always pointing to the current top of the stack, which is, let's say that we're in bar, SP is pointing right here. It's holding this exact address, the last thing, the top of the stack, all right? And then also, weird idea, SP can only be, for us at least, a multiple of 16. So we have to always keep SP a multiple of 16 when we're doing stuff. So maybe I need to like add to this diagram in a second. But let's say like we are like maybe bar calls another function, or in that function call we need to save the return address. We need to save like one of those saved registers that we were talking about a little bit before. If we ever want to save like a register's value, maybe LR or like a saved register like X19, if we ever want to save that as a local variable, we need to subtract from SP, right? Make SP smaller, make it go up here, the top of the stack up here, which is emptiness. Does that make sense? And you just subtract at least 16 from SP. And then you can store things, all right? So I guess I'll have to do this on the fly, forgive me. I need to add a new little line here. Insert row above. There's my empty slot. Boop. That's my best diagram. I think I did. I think I got away. I didn't, did I? Something went wrong. Oh no, this is good. So this is 0xef00. This is more emptiness. All right. And so if you want to store something, SP, you can't just like subtract 8 from it. So you really have to, like, if you want to do that, you have to subtract 16 from SP, put it here, and now you can like go to SP at 0 offset or at 8 offset, 8 bytes offset, and store something here or here. Or if you have even smaller stuff like 4-byte things, you can store them in between. But that's kind of how that needs to work. All right, so SP can only be a multiple of 16, and then you can start saving stuff. If you want to save it like this, subtract 16 from SP, like you can save it right here, and that's kind of what we just did. That would be the old X19, if you were to follow the store instruction, given what we just said, after we subtract 16. That's how it works, all right? That's how that works, okay? So I hope that makes sense to you. And now, if you go back to those programs that I wrote before, it should make a whole lot more sense too, okay? So, with that in mind, now that we know all this magic, it's not magic anymore, here is a question for you to try, all right? Let's say that we've got some assembly code. Here's my assembly code. We're in, let's say that we're in the main function right now, right? Let's say this assembly code is part of the main function. And remember that each piece of assembly code lives in memory. Each instruction has an address. Each address takes up 4 bytes. So like here's the instruction, here's where it lived in memory. Here's another instruction, here's where it lives in memory, all that stuff. And let's say that main is about to call foo. So here's the line that we're zooming in on, this line right here. So main is calling foo on this line, this instruction at this address. When foo gets called on the second line, what is the return value? Or sorry, the return address? What's the address that foo needs to return to? Because because foo needs to return back to main, right? Foo needs to do its own stuff. Foo, save its own stuff, return back to main eventually. Where does it return to? What's the address that it needs to store in LR? And eventually maybe push into the stack. Do you see it? And like, you can understand what's going on here, right? These are like, you can translate this to C++ too. Like this is like setting some local variable maybe to 42. This is calling foo with x0. So it's like foo call with 42 maybe. It's like, this is the call that we care about right now. What needs to happen after that? What line do we want to run after that? It's like, all right, this is like x0 plus plus or something. x0 plus plus. And this is like, if x0 is less than x7 or something. We don't know exactly what we're comparing, but like this is what the code looks like. What line do you want to run after foo returns? Well, it better be this line. Does that make sense? This is the line you need to remember and get back to. That's the line that needs to happen after the foo function returns. And so, what is its address in memory? AB48. Does that make sense? That's what's going to be placed in LR. LR is going to have AB48 shoved into it, because that's exactly where foo needs to return to, and that's how it knows where to return back to. Okay? That's the code. That's how that works. Okay? So, yeah, with all that, now the stack and local memory and all that fun stuff should be a little less scary, and we can now learn how to write our own functions and call them in a way that respects that ABI, that application binary interface. All right? So let's go back to how we write our own functions. Okay? So first of all, when we write our own functions, just like we did for the main function, you got to say like it's a global label, it's a special label, it's a function, really. It's meant to be interpreted as a function, not just a normal place that you could like branch to. It's cooler than that. And then you give a label with the same name. Okay, so that's how that works. That's how you create a function in assembly. If you ever want to call a function, remember that you can pass arguments in x0 through x7. That'll give you 8, right? Those are your first 8 arguments, can go in x0 through x7. And then the rest, if you need more arguments than that, you don't put them in registers anymore. If you want to pass like, you want like a 10 argument function or something, everything after the 8th argument needs to go on the stack. So you're forced to use the stack, forced to push to the stack in opposite order, okay? In opposite order, so that like, you push like argument, let's see, you push argument, let's say you have like a 10 argument function. You're going to push argument 10 first, because that's the last thing. And then you push argument 9 after that, because that'll let argument 9 be the first thing on the stack, the first thing you could pop off. That's how we do it. That's how we've decided to do it. That's what we agreed upon for the ABI. All right, so the topmost element on the stack will be the next argument, argument 9, then underneath it is getting bigger in memory, right? The stack grows downwards towards lower addresses, and so if you want to go and look beneath something on the stack, it's towards higher addresses. That's how that works. So like SP plus 8 would be argument 10, and then you can go even further down there if you add more stuff, okay? But you push them in reverse order, and even if you're adding ints, even if you're passing along integers, for an interesting, weird ABI reason that I don't know the full story behind, although ints take up only 4 bytes, we're separating them by 8 bytes each on the stack. So there's like some padding going on, we say. Okay, so that's something. And then if you ever want to return something, if you're returning something from your function, it returns like an int or something, then the return value goes in W0. If you're returning like a long, something that is 8 bytes, then you put the value in the full x0. But it's the x0 register, or part of it, holds the return value. And then your job is to return to the address that was given to you in LR as you got here, as you got to this function. Because the second you call a BL, it'll jump to that place, to that wherever foo was in memory, it jumps to that label, and it sets LR as well, where you need to get back to. It's the link register. It links 2 functions together. All right. And yeah, you go back there with a ret instruction. You may have to restore the old value if you yourself call functions, because that will clobber LR. All right. That is the technical term, by the way, clobber, which is funny. So yeah, I'll show you some code soon. We'll do a 10 argument function, I promise. You'll get some practice, but I just need to say some more words and have you think about it a bit more. Okay. So given what I just said, let's pretend we do have a 10 argument function. It's called foo. I'm passing along these values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, in those arguments. Given what I said here, pause here and stare for a second, how would you call it? How would you call this foo function? All right? You want to make this call as if you did this in C or C++. How would you do it? What's the correct register / memory arrangement to call foo? You don't have to actually do the assembly if you don't want to. Just like tell me what's in the registers, like draw a diagram. What does the registers look like, and what does the stack look like? All right? So given the ABI, how does it work? How does this foo call happen? All right, so we're eventually, we got some code, and we eventually hit, we have to do some stuff to manipulate both the registers and the stack, and then we say BL foo. So what needs to go here? How do registers and memory need to get changed? And so, all right, our first 8 arguments go in registers. So x0, let's say these are all longs or something. So x0 is going to hold 1. x1 will hold 2, x2 will hold 3, x3 will hold 4, x4, x5, x6, x7, right? That's what we go up to. Those hold what we expect them to hold. 5, 6, 7, 8. So the first 8 parameters go like that. You have to move into those registers. And then the 9 and 10, we have to use the stack, and we push to the stack in opposite order. All right, so here's what the stack looks like before. Here's my original stack that I start with before I make this call. Then I'm going to push 9 and 10 in opposite order. All right, so I'm going to push 9, I'm going to push 10, sorry. And then I'm going to push 9, opposite order. And then here's SP pointing to the 9. All right, that's how that works. And then also, once you're done, you have to clean up the stack, by the way. You also have to clean up the stack after you call the function. You need to do that afterwards. All right, so that's everything that I wanted to say, at least. All right, does that make sense? That's what everything should look like before you BL foo. And then you did mess with the stack, you should probably clean it up, right, when you're done. Because otherwise, the offsets will be weird for everybody else. Okay, so yeah. Again, remember that SP should always be a multiple of 16. That's important. And then if you put anything on the stack ever, you have to clean it up. If not, after you call that function, if it was part of a parameter, but at least before you return from the function, because let's pretend bar forgot to clean things up. Foo thought SP plus 8 was my return address, but no, now it's bar's old return addresses. It's weird stuff. The offsets are all wrong if you forget to clean up and move SP back to where you needed it to be. Does that make sense? It needs to be moved back to right here once bar returns. Does that make sense? That's how that works. That's how that needs to work. You always have to clean up after yourself, because the stack should look like it was at the entry of the function, because that's how it looked to the person who called you, right? They were memorizing the offsets, all the offsets for their version of the stack. And if you change SP and you don't restore it, then you've moved the offsets. Does that make sense? So that's very important, because if you had if you push something on the stack, there used to be a return address here, and then you push your own little variable. If you forget to do this, if you forget to clean up after the stack, somebody who thought this was their return address at the top of the stack sees some other old dummy variable that wasn't part of their own function. So that's a little disgusting, all right? And so then you'll return to a weird place that probably doesn't belong to your program even, and that's just a recipe for a seg fault, right? So we don't like that. So that is more stuff about the ABI. And now let me give you a function. All right, so let's make a function finally. Let's make it be called sum10, all right? It'll take 10 parameters, and it'll just sum them all up and return back the result, all right, in W0, let's say it's a bunch of ints, okay? And we'll call it from a C main function. I'll show you how to do all that, okay? So let's make a sum10 function, and here's how it'll work. Dun, dun, dun. So here we go. Let me make a new file called sum10.s, and again, I need all this stuff, right? I need to I'm making a function. I got all these things, right? Global the thing. It's going to be called sum10, global sum10. And what is the type of sum10? %sign function for a weird reason. Marks that it's a function, and then we actually give the sum10 label, and then we can start filling it in. Okay, so there's that. And then I want to like be able to use this function from a C file, so let's also make a C file. Where do I want to be? This one. Excuse me. I want to be here. So let's make a test sum10.c file, and it'll call the actual function. Okay, so here's include. We want to print stuff, so let's include the C version for printing, standard io.h int main, and then return 0. And we're going to call a function. Let's declare the function that we're about to write. It's called int sum10. Right? It takes 10 things. How many letters are? Let's just start with int A, int B. How many of these do I need? A, B, C, D, E, F, G, H, I, J. I need to go up to J. Int D, int E, int F, int G, int H, int I, int J. So hopefully I did the right amount and I didn't skip a letter, but like that's that. And then we're gonna call it sum10. So we're gonna say just put it in a variable or something. Int res equals sum10 on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Bam. And then let's printf that answer. Printf %d new line that result. Okay. So that's how we want to use it, and then we just need to implement the sum10 function now. So let's go and do it. So again, sum10, this is really what we're programming. This is the label, and it corresponds to this function in CLand. And so we've been given, right, when we get jumped to here, right, this is going to turn into a BL call, right, BL sum10, and it's going to have put everything in the right spot for these values, 1 through 10. So, all right, the first 8 args. Let's remember what's going on here. 10, 10, 10. So like the first 8 arguments are going in x0 through x7, and then the last 2 are on the stack in opposite order. All right, all that fun stuff. Now we're remembering it. Remember this diagram. Okay, we've got the first 8 args are in x0 through x7, but really for us, because these are ints, they're going in w0 through w7. In our case, it's w0 through w7. Same difference though. And then the rest are on the stack in reverse order. Okay? And so we're going to have to use the stack. We're actually not going to save LR because we're not going to call any functions within the sum10 function. So, all right, I need an answer, and the answer needs to be an int, and we're returning an int, right? So we're returning an int, and it's going in x0. x0 is where your return value goes if it needs 8 bytes, but we only need 4. We need to return an int, so it's going to go in w0. Right? So our answer is going in w0. So I just need to add into w0. So add into w0. Well, we already have like a in w0. We'll just keep on adding into a, for example. So add into w0 a plus b, so itself, right? w0 plus w1. And then add in also the C into W0. C is in W2. D is in W3. I think you get the idea now, right? W4, 5, 6, and 7. Those are the first 8 arguments. They've all been added into W0 now, right? Just add into W0 a bunch of times. And now we've got to deal with I and J, okay? So everything's been pushed in opposite order. So I is the thing on top of the stack right now. I is on the top of the stack. It's what SP is pointing to. All right, so let's get it off the top of the stack. So I would like to load into a register that I don't need it right now, like a scratch register. W1 I've already used, I don't need it anymore. Let's overwrite it with whatever's on the top of the stack. And so I'm reading from SP I'm reading 4 bytes on the top of SP into W1. That's how that works, all right? and then we're good. And then I've got this value, I need to add it in to W0, because that's where I'm storing the answer. So add into W0, W1, and then J, right? J is right below I on the stack. But for, even though it's a 4-byte thing, it's not SP plus 4, it's SP plus 8. But 8 bytes away for silly reasons. The reason is called alignment, by the way, if you want to look into that word. Alignment reasons. But it's silly to us right now, though. So where is it? Let's just kind of do the same thing. It's offset SP by 8 bytes. But still read a 4-byte value. This is just an int, all right? And that goes into W0 again. And then the result goes in W0. And we already put it there, right? We've taken care to put everything we wanted in W0 already. And then we just want to return, right? Return by jumping to wherever LR is telling us to go to. So jumping to, how do I want to say this? Jumping to the address in LR. All right, and that, remember, if we want to talk about more registers, recall that that is going to change PC, all right? That's going to setting PC to LR. That'll jump to that place. That's what it means. PC is short for the program counter register. It stores the address of the instruction I'd like to go in and be running. That's what the ret instruction is going to do. It's going to set PC to LR, essentially. And that is going to be our sum10 function. All right, I hope that makes sense. We were using our arguments, and it's the caller's job to clean up the stack. We don't have to mess with the stack because we never subtracted from SP. We never added anything of our own to the stack. We just used our own scratch registers. We're good there. Okay, so that was sum10, and here I am in the C file using it. And then I think that's what I wanted to show you. Whee. There. So let's compile and run this. So it's going to be GCC, give both things, test sum10, and then sum10. I'll call this, I guess I'll call it the final executable file, test sum10. And what is the sum of all the numbers from 1 to 10? Is it 55? I think so. It's 11 times 10 over 2, so 11 times 5. Yeah, that's 55. And so we did it. Good job, us. All right? And so that was a good taste of our first function in assembly. All right? One that makes a little bit more sense, hopefully. All right, so here's a little bit more information about calling functions, because actually it was main that was doing it for us. All right? It was main that was doing it for us right now. So secretly main was taking care of doing the BL sum10 and setting everything properly. Let's also get some practice with that, and let's remember what we need to do there. Okay, so here's what you do when you call a function. Let's remember. All right, and I'm going to add some information here too. So you got to put everything in the right place, like put all your arguments in the proper registers, or push them on the stack if you need to, if you have more than 8, and then x0 through x8, if you remember the diagram from the very beginning of the class, go back to that lecture. X0 through x18 are our scratch registers. Those are registers that anybody, including functions that you call, are allowed to mess with and clobber and never restore. That's just for scratch work, all right? So if you need these values that you currently have in your x0 through x18, any of those guys, if you ever need them after you call a function, because they might get clobbered and messed with, you better save them either in a saved register or on the stack. All right, these are your scratch registers. So the function that you're calling, the fancy word for that is the callee, the person who is being called by you, gets to mess with those registers, these scratch registers, all they want. They can, like, definitely x0 through x7 are going to get changed because those might be arguments, but the callee gets to clobber them all they want, like we were doing here. Like we were messing with, this is really part of x0 through x8, so we were messing with our own arguments, right? Or changing w0, changing w1. We're allowed to do that. Those are scratch registers, all right? Everybody else, all the other registers, they don't get touched, or if they do, they get restored, thanks to everybody agreeing to follow the ABI, the application binary interface, okay? So that's how that works, okay? So that's how that works. And I think that's what I wanted to show you there. So yeah, then you can do your BL. Then you can do your BL function name and kind of do everything you need it to do. And so what main did for us, we're going to do it ourselves in just a second, but the sum10 call, you got to set all the registers, and you also have to set the stack, right? Because you're calling it with 9 and 10 as well. Those are getting pushed to the stack in opposite order. So you have your original stack, and then you have your new stack. You got to push argument 10 and argument 9 as well, opposite order. All right, so SP is pointing here, and this is, I don't know, whatever value this is. Maybe this is address, or I don't know. Let's pretend this is address 0, offset 0, and then this is going to be, for weird reasons, offset 8 from your SP. Okay, that's how that works. So I hope that makes enough sense, even though it's an int. And then, once you've made the function call, you should probably, if you use the stack for arguments, you should clean them up. You should pop them off, because everybody else in your program is going to remember the old places where everything was. And yeah, then the return value, if there was one, and there is with our function, it's getting an answer back. You can look at that return value. It's being placed in x0 or w0 for us if it's an integer. So we got that, and yeah, let's do that. Let's do that ourselves. Let's translate our C main function to an assembly main function. Won't that be fun? All right, let's make that work. Dun, dun, dun. So we're gonna change this into test sum10.s. Won't that be fun? .s. And so let's make a main function now. Boop. Paste most of this. So let's see. We eventually want to return 0. Dun, dun, dun. Let's just do it all right, for fun. So this is all going to be not sum10 anymore. It's main, please. There. So what does the main function need to do? Well, we need to call a function. Right? We are in main. We are calling a function. We're going to do BL somewhere eventually. We're eventually going to do BL sum10, right? And that's going to mess with LR. And so we need to remember what our old LR was, because main needs to remember that we have the underscore start function to return to. We need to go back there somewhere. It's not whatever this is changing it to. So we need to remember our old value of LR. So we need to make space on the stack for it. All right, so sub SP 16. It's always 16, even if you're storing 8 bytes. All right, always got to be a multiple of 16. Let's save our LR. Store our current value of LR into like the top of the stack now. Okay, and then now we're ready to call sum10, because we will be able to get out our old LR value. All right. So what I want to do is call sum10 with the arguments we were using before, like these guys, right? And print out the result. All right. So what do we need to do? We need to set the registers, first of all. If I want to call it with, where is it? This one again. 1 through 10, right? So 1 through 8 are going in W0 through W7, because they're just ints. So move into W0, the number 1, move into, let's see if I can do this quickly in fancy Vim stuff. So let's do that. I'm going to attempt at least. Doop. And then paste. Quit. No, I did it wrong. Sorry. Whatever. 2, 3, and then 3, 4. There's got to be a way to do this better. That. And then yank, right? Or no, undo. Quit. I think that was my problem. No, I can't do it. I'm under too much pressure. Never mind, we'll just do it manually. So there are my values. They're in the right registers. And now the last 2 arguments, add the last 2 args on the stack in reverse order. So I got more stuff to put on the stack, okay? So, and each int, even though it's an int, everything we're pushing, taking up 8 bytes per push, if that makes sense. All right, so if I want to add two things, I need to subtract 16 again from SP. Sub SP 16. So I just made 16 bytes of space on the stack. Okay, and then I need to put some stuff up there. So I'm using W0 through W7 right now. I do not want to change those. So let's use W8, I guess, to get what I need into the right place on the stack. So move, let's do W8. That's number 9. That's the thing I need to put on the stack. And I need to store the thing there, store that number 9 onto the top of the stack, right? Because that's the next thing. It's in reverse order. So top of the stack goes there. And then let's do the same for 10. So let's use W8 to get through there. So store 10 now into SP plus 8. Okay. So now that's lower on the stack compared to the 9. So it's been pushed in reverse order. And then we can make the call. BL sum 10. All right. A lot of work. So that jumps us over to here. It'll do all the fancy work. Clobbering registers, right? They were scratch registers. At least we don't care. And then we're getting returned back to ourselves down here. Oops, too many BLs. Just one. And now the answer, because we put it there, right? We put it there. It's in W0. It is in W0. And let's see. We need to use it. Eventually we want to make like a call to printf, but we should also start cleaning up the stack, because we messed with the stack for just this function call. So let's clean up the stack. Clean up the stack. Everything we did for this function call was we used 16 bytes of stack memory. Let's, instead of subbing, let's add back to SP. Oops. Add 16 back to SP, and that will have cleaned up. Like, the stuff is still there, but they can be, like, that space can be reclaimed now. We just moved the pointer to say what's the top of the stack again. All right, it's the old stuff. All right, so that's SP back to how it was before the call, not before the function started, because we did other stuff. We saved LR as well. But the call itself did some stuff with SP. We cleaned up the call that we just made. And now we can use the answer, right? Let's see. We want to print it out, don't we? So let's take, let's in our data section, let's add a format string here. So format string is C string, ask is %d new line. And then I want to do a BL printf with the format string goes in X0, right? But W0 is what we want to print, and we just clobbered it when we did that, so we better move it into where it needs to go, which is argument 2 of printf. So W1 is where it needs to live. So move into W1, W0, and then I can clobber X0 to my heart's content, and then make the printf call. So here's the first argument. Second argument goes in W1, which is the thing that we got back from sum 10. All right, and then I think that should do it. So if I gcc test sum10.s now, along with the old sum10.s, it should be okay, I think. Nice. And do we still get 55? We do, but I seg faulted. So I messed something up, and that's because I forgot to do everything after this call. I was too eager, I'm sorry. So yeah, I seg faulted because like we started to run the format string as an instruction because I didn't return from main yet. Silly me, all right? So now we need to return from main. So we need to, what's our return value? We need to return 0. And then we need to restore the old LR value. So LR is at the top of SP right now. So load from the top of SP into LR. We subtracted 16 bytes from the stack to have space for storing that LR. Let's add it back to clean up the stack. Now the stack is right as it was before we got to this function, before main was called. Perfect. And now we're ready to return to whatever is in LR. Beautiful. All right. So as long as we do that correctly, we're not going to get a seg fault. Beautiful. But yeah, always remember to return or do the exit syscall if you're not having a main function, because like what just happened was if I didn't have this code, it just like fell through to whatever was here, and it kind of like, you could think of it as trying to run this string almost as an instruction, and obviously that instruction makes no sense at all. So hopefully that makes a little bit of sense. That's not exactly what's happening, but it's falling through to garbage memory, more or less. All right, no real instructions anymore. So yeah, that's our main function, and here's our other function. That is, I think, everything that I wanted to show you about all that. Yeah, remember, there will come a time, and I'll give examples of that later, But there will come a time where we need to use saved registers, something outside of this, or like it's X19 through X27, I think. Those are saved registers. You're guaranteed to keep those around between calls, and so you can put stuff there like I'm forcing you to do in your lab. So you'll get some experience for sure. All right. Before I switch gears, I would like to just show you how to do the same thing from C++ rather than from C. Like I made this little sample program, this testing program in C, and we called our own function sum10 that was like written in assembly. Just by declaring it, we were able to link it properly. It all worked. Let's do the same in C++. Calling assembly functions from C was very nice and easy, but C++ sadly likes to ruin our day. And the issue is name mangling, because in C++ it's not like BL sum10 anymore. It's like BL underscore Z sum10, and then it has like words that describe that each of these 10 arguments is an int. Like all that weird stuff is going on. And so if you'd like to just use a normal label like we were using, like have it BL to just something called normal sum10, then we have to turn off name mangling for that particular function. We have to declare it to be a C-style function, right? We're going to declare our function in C++ as this. We have to say extern C within double quotes, and then we declare our function. And then it will BL just blah, rather than BL weird underscore Z blah, whatever, all right? That makes sure it calls it without the mangledness, all right? So let's make a test sum10.cpp file now to call our sum10 function, remembering to declare it like this with extern, and then everything should work out. Okay? So I will steal the C file, because I can use most of that, and I'll make test sum10.cpp, and I'll steal all of this. So I need to declare everything still. Boop. I need to call it still, but I'll use cout this time. And like, I only want one main function, of course. Come on. There we go. And so here's how you do it. We're going to say, then I'm going to cout res. Okay, so that's how I want the program to really work. And here's how we do it. So it's going to be extern C within quotes, and then it's happy about everything. Now when I link it, everybody's cool. All right, so it's going to be g++ test sum10.cpp with sum10.s. Now it's happy. Test sum10. I'll call the output file test sum10cpp, I guess. And we do get the 55. It's happy, and so it's able to BL properly. That's how that works. Okay, because otherwise it's going to do something weird. Okay, so I think we're good now. I think that's what I wanted to show you. All right, let's keep on trucking. I've got more stuff to say. Let's talk about different places in memory, because the stack is a place in memory. The instructions, talked about those are stored in a separate place in memory than the stack. Those separate places are called segments. All right, so we should talk about them. What are our memory segments? Here's what they look like. All right, so there's a bunch of different sections. We know about the data section. We know about the stack. We know about the code section is called the text section. You remember me saying that before? But yeah, here's what happens when your program gets loaded into memory. All right, there are different places for things, right? Different sections or segments for the different pieces of your code. All right, the text section is the code itself. That's the assembly instructions in machine code format, and that is a read-only memory segment. You cannot change your code instructions as it's running. So here's what your program looks like as it gets loaded into memory. This is here are low addresses, like this is like the 0 address, and like here are these are high addresses up here, like this is FFFF, big addresses, right? So your text starts down here. Here's where your program begins. It's a read-only segment of memory, and then there's the data section. All right, there's the data section. There's actually a secret place that's uninitialized data. We have an initialized data section as well as that. The data section is initialized to stuff like we were able to initialize our data to or something with a printf. Like we actually give a value for this format string. That's initialized data goes there. And there's also an uninitialized data section that I haven't shown you how to use. We don't really need it in this class, but that's there. All your global vars go there, essentially, one or the other. and then you have the stack and the heap, right? So after those, the stack and the heap, like the stack starts here at the high addresses and starts growing down towards lower addresses, and then the heap fights for that same place in memory. The heap is your dynamically allocated stuff. The heap fights for that same place in memory, and the heap grows up towards higher addresses. So as you allocate stuff on the heap, like the heap pointer kind of grows. Just as you call functions and make local variables, the stack pointer grows downwards, all right? If they ever clash, they share the same segment of memory. If they ever clash, like the top of the stack meets the top of the heap, you obviously have run out of memory, and then you get a seg fault, okay? That's what we want to make sure never happens. So we want to clean up after ourselves, in theory, all right, if we can. So yeah, I've shown you everything but really the heap, okay? So let me show you how to allocate stuff on the heap in assembly. We're going to use the C library for that, all right? So the C library way of doing allocation on the heap is there's a function called malloc, and there's a function to deallocate called free. This all lives in the standard library file, standardlib.h, okay? C stood lib from C++, right? So in C++, we have new and delete for heap stuff, but in C, you can actually use it in C++ too. It's malloc and free, all right? Those are two functions that do the allocation for us. And actually, a lot of C++ compilers, potentially even G++, I forget, inside of new, like the way new is implemented, they call malloc. So it's like, that's what's really happening. And then malloc is, of course, making like a syscall to actually do the real, tell the operating system I want memory. But we'll stop here. All right, so C stood lib, so standard library.h. That one, you got your malloc and you got your free. Here they all are, right? So malloc. What malloc does is it takes how many bytes you would like to allocate as its one argument, and it gives you back a pointer to that thing, all right? Void star just means a pointer to memory that doesn't have a type, like it's at whatever type you needed it to be, all right? That's what that means. So, yeah. Instead of saying then, new int in C++, in assembly or C, you would say malloc the size of an int, which is 4 bytes. Does that make sense? So yeah, malloc with a certain size allocates that many bytes on the heap and gives you back a pointer to the start of those bytes. And then free takes a pointer to somewhere that you've malloced on the heap. Malloc stands for memory allocation. It takes a pointer and then it frees that memory, okay? So malloc and free go together just like new and delete go together. So instead of saying delete p, just like you did in C++, that corresponds to calling free on the pointer. That's the similarity there, okay? So, all right. Before I give you an example of malloc, let's pretend, you try this. Let's say that we want to allocate an array of 3 doubles. 3 doubles on the heap. Remember that each double is, remember which size of doubles are, how many bytes is in a double. Go look that up if you forget. What should be the correct call to malloc? How many bytes do I allocate? And like what type should it be? Should it be this kind of thing, this kind of thing? See if you can figure it out. Because an array is contiguous memory. How much contiguous memory do we want to store 3 doubles? All right. First of all, a double is 8 bytes each. So how many bytes total do we want here? It's going to be 24 bytes, so that we can definitely cross off these guys and that one. Hopefully that's not you. And then it's either, is the syntax like this or like this? And remember that malloc is always going to give you back a pointer to the start of that memory. And so you can use that as an array with the array-like syntax if it really is one. And so the answer is going to be D, all right? You're always getting a pointer back. So this style of syntax doesn't work unless you're like on the fly declaring an array like this and the compiler can see it. Okay, so that's how that'll work. So just like look, it'll give you back the starting address and you can use that like an array. All right, so let me show you an example with ints instead. Let's allocate an array of 3 ints, use it, and free it. All right, and I highly encourage you to convert what I'm about to do into assembly. So let's, what should I call this? I'll just call it like malloc.c. It'll be a C file. we have to do C stuff. Standard IO.h int main. And then because I'm going to do malloc and free, I'm going to use standard lib.h as well. All right, so let's do stuff. Got to return 0 eventually. So I need to make an array on the heap. So using the same syntax that we just kind of figured out together, it's going to be, I want an array of 3 ints, right? So I'm going to say malloc, 3 ints is 12 bytes. You can say malloc 12, or you don't even have to remember. You can just be like 3 times however big size of an int is. That's pretty nice, isn't it? So this makes an array of 3 ints on the heap. And we want to store that into a pointer, right? Int star r. What's the start of that place? And you can use this like an array if it really is one, and it really will be. It's got 3 ints. So indices 0, 1, and 2 are fair game to use. And I forgot to add a semicolon. There we go. So, all right, let's use this array now. I've got, let's set it, r of 0, let's set it to like 1, r of 1, let's set it to 2, r of 2, let's set it to 3, and then let's just like do something weird with the arrays, like sum up all the values or something. Printf %d new line, so we'll print an int out, and that int will be the sum of r of 0 plus r of 1 plus r of 2. All right, so I got that, and then that's all I want to do with my array, so let's free it. We'll be good C programmers. So you give the pointer to the start of the array, which is just you call r, right? You just say r by itself, that's the pointer, and that should do it. So gcc malloc -o malloc, and bam, the sum of 1, 2, and 3 is 6. Cool, huh? So that's heap stuff, and so you can do the same thing. You'll just like bl malloc, bl free kind of stuff. You can do it all in assembly as well. All right. And so I think the last thing I want to talk about today, now that we know how to like make main functions and call other functions for real in assembly, let's just play around with the C standard library. The word that people like to use to describe that, it's called libc for short. It's the C library. It's everything we've been using. It's malloc, it's free, it's anything in the C library. All this stuff is kind of like included automatically for us whenever we like compile an assembly program with GCC. So it's all there. We get printf and other things. So yeah, let's get some examples up in here. Let's do let's do one silly example. Let's get a number from the user. I'll show you how to do that in assembly, and we'll print if it's greater than or equal to 42. All right. We're going to have to use the stack because the way that you get a thing from the user is to use the scanf function, and you need to provide memory. So I guess we could have used the data section, but we're going to use the stack instead. All right. Let's see here. So yeah, C standard IO, so standard IO.h. In addition to printf, it has scanf. There it is. That reads things. So you give a format string that describes what you want to get, and then you give like the address of the memory that you want to read into. All right, if that makes sense. Like here's how you, surely there's one that asks for an int. Yeah, here's how you use it with an int. You say scanf %d, and that'll have it look for an int in the input, and it will write to memory. So you give an address of what you want to write into. Okay, so that's how that works. So let's do that. Let's do that in assembly. So we're just going to get a number from the user as an int and figure out if it's greater than or equal to 42, right? Using the stack. So can I steal a main function? That would be nice. Main function in assembly stolen. Let's call this ge42.s. Greater than or equal to 42. So let's get rid of everything else. I don't need any of this. I will eventually be calling printf, but we'll deal with that later. I'm going to call other functions, so I need to keep LR saved. And so now let's get a number from the user, and store it on the stack. All right. So let's make room on the stack for one new integer. Make room on the stack for one new int, and that's going to be 4 bytes of information. So technically, honestly, we could use the rest of SP because we're only storing LR right there. So that actually might be fine. So actually, we already have room on the stack for one new int. We can use, for example, we can use SP plus 8, right? Because that's not in use right now. We're only just using SP in the first 8 bytes, right? We're always subtracting 16 from SP, so we've kind of wasted some space. Let's not waste that space anymore. So that's SP plus 8. We only need 4 bytes though. Every int is 4 bytes. So that's fine. So we'll just use that. All right. So that's that. And so let's call scanf. We're eventually going to call scanf, bl scanf, and the format string for scanf, it'll be a bit different. It's not a new line. It just takes %d. Like, it's implicit that you're going to type new line when you're done typing. So it's just %d, the format string for scanf, and so that's going to go in x0. And then the address, the next argument to scanf, it's like we're doing this. We're saying we want to call scanf format string. It's like %d, and then the address of that integer that I want to read into. Okay, something like that. So this is kind of how that works. So x1 is going to be the address, right? So how do I want to put it there? It's essentially into x1 goes the address of the place in SP that I want to use, the address in relative to SP. That's going to be the place where I store this. So it's SP plus 8. So I can use an add instruction. Add SP and 8. Whatever you get there is the address that I want to store into. That's x1. That needs to go there. And then I can BL scanf. Does that make sense? I hope that makes sense. So that's the idea. Okay, so then I've got there. And then now, after scanf has returned, SP plus 8 has been set to whatever the user types. The user typed. Let's read it in to a register. Let's put it in, let's say W0, because it's an int. And then also, yeah, that's what we wanted to do. If we allocated stack memory right here just for the scanf call, so we wanted to put it somewhere, after you read it out and put it in your register, you could maybe clean up the stack, but we want to keep the stack as it is. We just put it here, okay? That's how that works. Honestly, it might be helpful. It might be more helpful for me to just make new memory on the stack. I think I'm going to change up this example if you'll let me. All right, this will work for sure, but let's store it on the stack. All right, we could use this. We could use SP plus 8, but let's be wasteful for fun, just as an example. For fun, we'll allocate extra memory because one day you'll need to. So let's subtract another 16 bytes from the stack, all right? Let's do that, all right? We only need 4 bytes for an int, but we need to subtract a multiple of 16 always. All right, so sub SP16, and then now I could just use SP itself. I could do a move SP into x1, because the top of SP, right, can go right there. So I've just made new space. Wherever SP is pointing to right now, that's brand new fresh space that I could be using to store in it, right? So now SP, just itself, SP, the top of the stack, let's say, has been set to whatever the user type. Let's put it in W0 because it's an int. And then we'll also clean up the stack because we're done with that memory, okay? So that will be that. I think we're good there. And so let's load into W0 whatever SP is pointing to right now. Now I'm done with all that space that I made for myself on the stack. I'll add it back to SP to reclaim that space. Okay? And then now what was my job? What am I trying to do again? I'd like to compare that number that the user gave me to 42. So all right, let's compare. Compare what's in W0 to the number 42. And print something if it's like greater than or equal to 42. Print something else if it's not. All right, so let's say branch if it's greater than or equal to a GE42 label. All right, so here's like a GE42 label, And then if it wasn't greater than or equal to 42, that must mean it was the opposite. We would have fallen through. We can call that LT42. We don't even need a label, but just for us, the programmers, it's helpful. And so if it's less than 42, what do we want to do? We want to print out that it was less than 42. So let's make some strings. String 1 in the data section, C string, ask is greater than or equal to 42, new line, and then 1 for if it was less than 42, because that was the opposite comparison. So string 1 if it's bigger or equal to, string 2 if it's smaller. So I guess we want to print string 2 in the LT42 case. So let's load that into x0 string 2, and then we can BL printf it. And then we don't want to follow through and also print that it's greater than or equal to 42, so we need like a done label. So go to done immediately after we did that. BL done, always. And then if it was greater than 42, it's a string 1, right? Oops. String 1 that we print out with printf, and then we can just have that fall through and everything's golden. All right, and then we want to return 0, and that should do it. So let's see if I can show you this entire program at once. It looks like I can. Good. So there are all the lines. And so yeah, I get the thing with scanf, made room for it, put it in a register, and then did a comparison. Did some comparisons and actually worked with the data after I cleaned up the stack. Okay. So let's GCC it, GE42, because we're using the C standard library. We're using GCC, and that'll automatically link with it. We're using libc is another way to say it. And so, all right, let's enter a number. So 42 greater than or equal to 42. 44 also greater than or equal to 42. I don't know, 33 less than 42. Check our edge cases. 41 less than 42. Perfect. So yeah, we're good. That's a fun one. And then let's also do an example where we print 50 random numbers. Let's do like a loop, get practice with loops, the C standard library, and some of these functions. All right, so let's do that. Let's print a bunch of random numbers, and I'll show you how I think about it. All right, print 50 random numbers, and we'll have to seed our random number generator as well with srand times 0. Okay, so I'll show all that to you. That's also in C standard library. All right, remember all that? Not the time stuff, at least. But srand and rand, we're here. There they are. Just call rand to get a random number, but seed it first. And so, yeah, let's make that happen. I'll make a new file, steal all these guys. I'll call it printrand.s. Still, it's a main function. Still, I need to do all this stuff. Let's steal everything from here to here, and I'll eventually need a format string, so I'll keep that there, and we'll deal with it later. But here's a good start to everything. So now finally I can show you an example of using a saved register. So I'll prove that to you in a second. So let's do srand times 0 first of all. Srand times 0. I need to do that for sure to seed my random number generator. Otherwise it won't work properly. All right, so let's seed my random number generator by, well, I guess I first have to call times 0, and then I can call srand with the result. So move into x0, 0. That's the 0. That's the 0th argument to time. So I'm going to BL time. All right, and so that returned a value. The current time has just been returned to me in x0, which is perfect because that's where I need to place the argument when I'm calling srand. It's already there. So now I can just BL srand with whatever I got back. It's already in x0 as the first argument. So now I've just seeded my random number generator. Okay. So now I want to print 50 random numbers, and one thing I cannot do, because I'm going to call BL printf a lot, I cannot use scratch registers right now to keep track of, have I done 50 yet? Have I done 50 yet? Because printf, whenever I say BL printf, it's allowed to clobber all non-saved registers, all scratch registers. So, in order to keep my counter safe, I need to put it in a saved register, all right? So I need to count down from 50, let's say, or count up to 50. That needs to go in a special place, and that needs to be a saved register, all right? Where did I say that? Did I say any of this here? Yeah. I talked about the scratch registers. There are saved registers too, though. Let's go to here. I think it was these slides, so we're always going to be coming back here for reasons. Here are your saved registers right here, 19 to 28. Everybody's agreed to restore those if we ever clobber them. So let's put our counter in x19, all right? And that means we need to save the value, right? If we're messing with x19, we need to keep it as it was for whoever called us. So we're going to use x19, all right? Dun, dun, dun. So we're going to use a saved register, x19. So we ourselves need to save it so that it has been restored. We can restore it before we return. We have to save it so we can restore it before we return, because the other person who is also using that same x19 register before us, who called us, needs to see the same value. Everybody's agreed. Those are the saved registers. If we touch them, we must save them and restore them. Have to save it so we can restore before we return. All right. So there is space. We have LR saved in SP. We have another space for another 8 bytes in SP plus 8. So let's store x19 in SP plus 8. All right. So hopefully that makes sense. We need that. All right. We need to do that. And now we can print 50 random numbers, and we're good to go. All right. So print 50 random numbers. How do we do it? Well, we need a counter. Let's move into x19. This is going to be safe across printf calls. Let's start it with 0. All right. So again, let's explain it down here. So again, our counter variable needs to go in a saved register, or on the stack, honestly, but registers are easier, in a saved register, because the functions that we call within our own function, like printf, the functions that we call can clobber x0 through x18. We have to save and restore the original x19. Very, very important. All right, but now we're good. Now we can loop. All right, so let's make a loop label. Loop label. And at the start of every loop, we just want to see, are we done yet? Have we hit 50? So compare x19 to 50, and we're going from 0 to 49. So as long as it's less than, we're good. And so if it's ever greater than or equal to, we're done. Does that make sense? That's how I think of it. And so done will be down here. That'll like stop the program, return 0. There's my done. And all right, if I don't, if I'm not done yet, I need to get a random number. I need to call rand and print the number. All right. To call a function that takes no arguments, you don't have to worry about any registers at all. There's nothing to put anywhere. Just bl rand, and it will return to you that random number in. It's an int, I think, that it returns. So it's going to give it back to us in W0, but don't mark my words. Let's check that. Yeah, rand returns an int. It's not a long. So it's just 4 bytes. So rand returns an int. So we're looking in W0, not X0, right? And so let's print. Let's printf it, right? We want to essentially printf %d new line that result, rand result. All right. So where's my format string? I need that new line there. Add it back. And so I need my format string, load into X0, the format string, and then the rand result goes in X1, but right now it's in W0. I need to put it in W1 before I clobbered it. All right, so let's move into W1, W0, and then I'm good to replace the entire X0 register, and everything's safe, all right? And so there's that, and then, yeah, I want to get up to 50 on X19, and so printf is guaranteed to have restored x19, so my counter value is safe. It's in a saved register. I want to increment it. x19, x19, 1. It's like if I was in iteration 0, now I want to be in iteration 1 next time, and I want to jump up to the top of the loop. And eventually, it'll stop, and all will be well. All right, so there is my file, and I think that's most of it. Let's see, there's the start. Here's the loop onwards. And I think you can understand what's in the data section. So I'll just show you the code itself. And let's watch it work. Let's see if it works. GCC print rand.s-o print rand. And this is a good example of using saved registers. You're kind of forced to do it this time. And so I got 50 numbers printed out here. Hard to see, But we can make sure we weren't off by 1 by using the word count command. So it was 50 lines. So that's perfect. 50 separate numbers. All right, that's how that works. So yeah, print rand works, and it's different every time. The last number. Look at that last number, and let's confirm that it's different every time the time changes, because we're seeding that random number generator. Okay. So yeah, that's the C standard library. That's a great example of using saved registers as well, X19 through X27, I believe, you're allowed to use, and those are guaranteed to be saved across function calls. So every time, like, you're going to call printf, it's clobbering everything but X19 through X27. So in between those calls, that better be where you store your stuff, all right? Either there or the data section or the stack. So I think that is all that I wanted to show us for today's lecture. I've got some more things to say in some other videos, like a lab video, so you can go there and watch those. But yeah, that's all that I want to record for this particular video, at least. And so I'll see you in the next one, whatever it is.